All right, guys, so what we're looking at here is we're looking at some different tests to tell whether or not a series is going to be convergent or divergent, or at least something that's going to help us do that. If you remember what we talked about previously, we talked about P series. Now remember, a P series is just any series as we write it from 1 to infinity of 1 over n raised to some p power. And we can tell immediately whether or not the series is going to be convergent or divergent if p is less, if the absolute value, no, if p is less than or equal to 1, then we know that it's going to be divergent. If that power is bigger than 1, then we know that it is going to be convergent, okay, automatically by knowing that. So, but you might be saying, well, there's hardly any series in real life, and this is true. There are hardly any series in real life where we look at them and we say, oh, I know for a fact it's that simple. I know that it's going to be convergent, okay? But what we can do based on the fact that we have this rule about P series is we can look at more complicated series and compare the two together. In other words, if I know that one series converges and that series, every term in that series is bigger than a similar series, then I can automatically say that that series is going to converge. And if the opposite's true, if one of them diverges, then the other one must diverge as well in both of those instances. Now, really what that's saying is this. If you think about it like a series, most of the series that we're interested in right now, they look like this. They kind of come down and then they look like that. If we were to look at the function 1 over x, it would have that very similar look where it comes down and then it levels off right around 0. And when we were talking about P series, we said, okay, most P series get close to the x-axis, close enough that we can actually find out what that area is, other than our harmonic series, was just where P was 1. Okay? So basically what this is saying is if you know another function or another series where all of these dots are right below where these dots would be, and it doesn't have to be right below, but anywhere below, in other words, the values of each term in the series are a little bit less, then I can say that that series is convergent as well, okay? So here's kind of the way that you think about this. I've got 1 over n squared plus 5n. Now I know that the infinite series from 1 to infinity of 1 over n squared, I know that that series is convergent because the power on our P series right here, I can see that that power is bigger than 1. Well, if you think about this for just a second, on the bottom of this series, I've got n squared, and then I've got a little bit more every single time. And it might be a lot more depending on what the number is that we're looking at. Well, if I have 1 divided by a number, and I know that this series is going to be convergent, if I add a little more to the bottom term of every one of these fractions, every term that we look at on these are going to be smaller than the terms that I can see in this P series is already convergent. So as long as I know for a fact that all of these terms from this series are going to be smaller than all the terms from a P series that I already know converges, then I can say that this one is convergent as well, and we just say that we directly compared it to 1 over n squared, which is a P series that we know is convergent. Now, that idea at first seems really easy. Like, okay, basically, anytime I see n squared plus something on the bottom, I can say that it's convergent. The answer to that is yes. On this one, what we could compare this to is we could say, you know what, I've got a plus 1 and a plus 2, but when those terms get really, really large, the only part that really matters is the 3 to the n and the 5 to the n part. So really, I could compare that series to the series from n equals 1 to infinity of 3 to the n over 5 to the n, or that is really 3/5 to the nth power. That is a geometric series if you were to look at that one. And then I could tell immediately, so it's not a P series this time, but it's a geometric series, and I can see that the ratio from one term to the next is 3/5. Because I'm adding 2 to the bottom every single time, I am guaranteed that this series is going to be slightly smaller than this series right here. So because 3/5 to the nth power converges, and it's a geometric series, I will also know that this series converges as well. Now the only difference between the two is I know what this one's going to add up to because it's an actual geometric series. This one right here, you don't have a common term from one to the next. So although I know it converges, I will not know what it adds up to. So anytime you can compare it to something, so like anytime I have something to compare where I know for a fact that one term, every single term in one series is going to be smaller than another, I'm good to go. The problem is that's a very specific type of problem, again, that we're looking at. This problem, you'll notice, I am subtracting 3 minus n. So when I subtract 3 minus n, the reason why that kind of sucks is because I can't guarantee that 1 over n to the third, if I wanted to compare it to that every term in this series would be bigger than every term in this series. I think it would, but I don't know for a fact that that is going to happen. In fact, even if you look at the first term in this series, which starts at 3, this would be 1/27th. This one right here would be 1/18th. 1/18th is bigger than 1/27th, so automatically I can't use the comparison test. But what we can do instead is we can use a slightly different test. It seems similar at first. We use what is called the limit comparison test. Now, the limit comparison test is basically, it's an awful lot like the direct comparison test, but we have to take it a step further. Basically, what we do is we say, okay, I'm going to look at a series that I think I would compare that to. So over here, where I had 1 over n to the third minus 3n, I'm going to compare that to 1 over n to the third. I think those two functions are similar, and because this is a p series that I do know that it converges, because that power is bigger than 1, I think this one converges as well. Here's how you prove it using that. This is the formal definition. What you basically do is you make a fraction out of your two series, like a specific term in your series, and then you do the limit as n approaches infinity. Basically, what that's saying is, I want to look at a term that's way, way out there and see what fraction I actually get. If I get a number of some sort, okay, and it can be any number, as long as that number is a specific number, then whatever the one function does, so too the other function must do. Because basically, and what that's saying here is, if I were to compare this particular series to this particular series, I can see that they have similar characteristics as the terms get really, really big. In other words, like their horizontal asymptotes are the same for both of them. So these two series, if I create a ratio out of them, as the terms get really, really big, they're going to behave the same way, way out there on the graph. And if I get a specific number, that tells me that they behave the same. So back to this one, I know that it's going to behave very similarly to 1 over n to the third. So what I would do is I would do the limit as n approaches infinity, and you just do one of those series over the other one. And it doesn't matter which one goes over which. It really doesn't. Now I can see I've got a fraction divided by a fraction, so I'd multiply the bottom fraction up to the top, and then I would make a fraction out of it, n to the third minus 3n, and this is the limit as n approaches infinity. Now, we've talked about these before. That is just talking about what is the horizontal asymptote. Although it's not a function, it's a series, it still works the same. The power on top and bottom are the same, so I make a fraction out of their leading coefficients. I see that that number is a number, and it doesn't matter what it is. What that means is, because I got a specific number, because this series I know converges, so too does this series. Now, 100% honesty, most of the time you can just look at a series and tell whether or not it converges based on the power that like the degree of the polynomial on the bottom. So like this one right here, I can just look at that and I can see that. But what we're doing here is, if you're asked to use the limit comparison test, this is what you have to do. Okay, so here is another one. Okay, this right here looks awful. But if you think about it, because we're doing the limit as n approaches infinity, which is what that should be here, because we've got an infinite series, when I plug infinity in, only the highest powers on top and bottom matter. All the other terms just don't have enough size, if you will, to make any sort of difference on what we're looking at. So in reality, this function behaves roughly the same as 1 over n to the third. If I were to use the limit comparison test, I'd go limit as n approaches infinity of that entire function, series, I'm not going to write it again, over n to the third. Well, if that were the case, I would flip this fraction upside down and times it to the top, and then I would multiply n to the third in. So I'd get n to the fifth minus 2n to the fourth plus 7n to the third. The bottom stays the same, so I've got n to the fifth and a whole bunch of other stuff that doesn't matter because we're taking the limit as n approaches infinity. Once again, and this won't always be the case, but once again, the fraction that I get by looking at the highest powers on the top and the bottom, that's 1 over 1 because the powers are the same, fraction out of their leading coefficients. That gives me 1, which means that I know that this series is going to be convergent because 1 over n to the third is convergent, and I used the limit comparison test in order to tell. In general, the limit comparison test is very useful when you have one of these rational functions where it has n's on top and bottom, but nothing weird. There's no like exponential functions or logarithmic functions. This is where the limit comparison test is very useful. One thing that I want to call your attention to again, just like when we talked about the p-series, is that just because we know that it's convergent doesn't mean that we know what it converges to. Geometric series are the only kind of series that you can do that with. Again, direct comparison and limit comparison are very similar to each other. Direct comparison is much easier, and honestly, you can use the direct comparison test when things are only being added on the bottom of a fraction and it's 1 on top. So like 1 over n to the third plus 3n squared. I know for a fact because that's a plus and that's a 1, I can use the direct comparison test. If I have 1 over n to the third minus 3n squared, then I need to use the limit comparison test, which basically works the same. If you have any questions about this or anything else in this section, please let me know.